Hey there, everybody. So, today we have a fun video, first installment of my Dr. Eigenstate Explained series, as you can probably tell by the title. At least I hope you can. And again, as I'm sure you can tell by the title, at least hopefully, we are going to be talking about this guy right here. So, if you can't pick it up from the title, this little guy is called a wave function. I could actually be, if I was actually capable of writing an I there. Apparently I'm not. What exactly is a wave function? Before I answer that question, I want to give just a brief explainer as to why I wanted to make a video on specifically what the wave function in quantum mechanics is. And that is because a lot of people that talk about quantum mechanics that I have run across oftentimes don't fully understand what it is they're actually talking about. And the problem is, well, I guess the problem is that people don't really have a full understanding of what they're talking about, which, I mean, is, when you're dealing with a topic like quantum mechanics, that's something you're going to come across. It's something I want to clarify just briefly is quantum mechanics, in terms of the math, really isn't that hard. It's not going to be mathematically any more rigorous than classical mechanics. The thing that makes quantum mechanics difficult is the fact that it's non-intuitive. Where classical mechanics, you're looking at the equations, you're looking at what they're telling you, and you're like, that makes sense. You look at the equations of quantum mechanics, and the math is just fine. The math works. You can use the math to get results, but you're like, I don't understand how this works. So it comes as no surprise that when certain people talk about quantum mechanics, they might not have a full understanding of what exactly it is that they're talking about. And I think that explaining at least some of the concepts in quantum mechanics, and I'll touch on probably several in this series, I think a good place to start is with, if I could get back to my pencil, is with the wave function. That's lowercase, and then uppercase would look something like that. So what exactly is a wave function? Well, in technical terms, the wave function is a complex valued probability amplitude that can be used to derive the probability of a given measurement for a system. More colloquially speaking, what the wave function is it's this handy mathematical tool that allows us to figure out what the measurement of a system is. If we want to measure a system, what result are we going to get? The wave function is the thing that's going to tell us that. So just to start here, a term that I used is complex valued. And I'm not going to dive deep into the technicalities here, so if anybody's watching this that really understands this subject well, even better than I do, don't beat me up because I'm not being super technical. I will be somewhat technical, but I'm not trying to be extremely technical here. But the first term that I used is complex valued. What this means colloquially is essentially that the wave function is given by a complex number. Complex number would look something like a plus bi, where this is a real number, like 4, and this is an imaginary number, with that being the imaginary unit. So you could have 4 plus, it's supposed to be a 7. 4 plus 7i. Real number, imaginary number, the whole thing is a complex number. So that is what the term complex value means. Shorthand version of what complex value means. You can get into technicalities when you start getting into things like complex analysis or functional analysis. They've got all sorts of in my opinion, overly technical definitions of what a complex number or what a complex valued function is. A more technical definition is that a function is complex valued if and only if it is complex valued across its entire domain. I'm assuming most people watching this would assume or would remember from like pre-calculus and things like that, maybe even algebra 2, is that the domain of a function are all of the numbers that you can put into the function to get some other output number. And if all the numbers that you can put into a function are complex numbers, then the function is considered a complex valued function. The first thing in that's what a wave function is. It's this I guess you could say this number that allows us to figure out how we're going to measure a system, what quantities we're going to get when we measure that system. So that's what a wave function is. How do we use it? What exactly do we do with it in the equations to get those results? The very first thing I'd like to cover is something called and I apologize if some look bold and some don't. My Apple Pencil is pressure sensitive, so it's called the normalization. If I could spell correctly, that would be great. Normalization condition. The normalization condition. And what this is it's essentially a condition that the wave function must meet before it will actually work in your equations. If this condition is not met, your wave function isn't going to give you the results that you want it to give you. And we have a handy, I'm going to give you the equation for it. We do have a handy equation for it, and that is the integral. I know that looks like an S, but it's the integral from negative infinity to infinity for the absolute value of psi x t squared dx equals 1. I don't think I'm missing any terms there. If I am, oh well, we'll figure that out later. The integral from negative infinity to positive infinity, and that's what these two bars here mean. They represent absolute value, which essentially means that, so the absolute value of negative 3 and 3 is 3. So this is going to be a little bit simplistic, but it's a way of essentially making whatever is within the bars, the absolute value of the thing, is just making it sign independent. It's always making it a positive. And that's because we work with, I forgot the little parenthesis there, we work with complex numbers, complex conjugates in quantum mechanics. Everybody should know what a complex conjugate is. A plus bi, the complex conjugate of that, which is represented by a little star, would be A minus bi. So you're just reversing the sign of the complex number. That's all the complex conjugate really is. So what this equation might look a little intimidating, it's really not. All it is telling us is that technically you need to integrate over all possible states or all possible measurements of a state, and when you do so, they need to add up to 1. And if you think about this, when you're dealing with probabilities, that makes sense. If you've got, say, a coin, and you want to know when you flip a coin whether it's going to land on heads or tails, the first thing you need to establish is that both of those probabilities, heads and tails, added together should equal 1. 0.5 for heads and 0.5 for tails. You have 50% for heads and 50% for tails. You add that together, you get 100% or 1. So that is really all the normalization condition tells us, is that when you add up all the probabilities together, it should equal 1, just like if you add up the odds of the coin being heads and the odds of the coin being tails, with it being 0.5 or 50% for each, should equal 1. If it doesn't, you did something wrong, and you need to figure out what you did wrong and fix it. So that is called the normalization condition. And once a wave function meets that condition, it is called a normalized wave function. Sometimes that is abbreviated to the norm. Like the norm squared would be the normalized wave function, the square of the normalized wave function. So that is the first thing you need to do. You need to normalize your wave function. You need to ensure that all the probabilities that the wave function that you could derive out of the wave function, when you add them all together, you will get 1. That way you know that you're working in again, in simplistic terms, you're working with a complete system. You factored in all the possible outcomes that you have for the system. The next thing that's important to a wave function using it is something called, and again, I apologize for some letters being bold and some not. It's called the Born rule. Make that look more like an E. Which, the Born rule can be defined technically. I don't really think it needs to be, which even the technical definition really isn't that complicated. But it essentially states, what is that little thing doing there? The Born rule essentially states that, let me write that a little better. The probability, and this is something I got from the MIT courses on, MIT OpenCourseWare courses on lecture courses, I should say, on quantum mechanics. That's where I got that symbol from. Alan Adams teaches that course. Really, really great course. I might actually link that course in the description of this video just because it's a really good course. So that term means probability. That's all that term means. That the probability of any outcome, and I'm going to use the subscript I. That might not necessarily be accurate, but I don't care. We don't have to be accurate here. Always, anyway. That the probability of observing some state, and that state is I, is equal to the square. Actually, you know what? I probably shouldn't use I because this is going to get confusing. Let's just use, if I could stop making things bold, let's just use K. The probability of measuring some outcome is given by the square of that outcome. The square of that outcome in quotes. And this is a really simplistic description of what the Born rule is. It's telling us that if you want to actually get a measurement, and this is in more technical terms, you need to take the coefficient applied to the state vector, which is the thing that when you're actually mapping things in a particular type of coordinate space, it's called a Hilbert space, which is really just the space of all possible wave functions. When you're actually mapping, when you're actually mapping the wave function in a Hilbert space, you represent it with a vector, and that vector is called the state vector. So state vector really is just a fancy term for a wave function. If you want to know, what you have to do is, for every state, there is a state vector that would look something like that with, I suppose you could put psi in there. That is a state vector. Now you have some, and I'm going to use C, you have some coefficient that is generally a complex number attached to it. You take that complex number and you square it, and that gives you the probability of that particular outcome occurring. And that is essential. Really, what I could have just done here is use C. That probably would have been simpler. The probability of observing some outcome is equal to that outcome squared, simplistically put. And that's the Born rule. That is another very, very important thing that needs to be considered, because you don't really ever measure a wave function. You measure the square of it. In technical terms, the Born rule states that the probability of measuring some quantity or outcome for the system is given by the square of the amplitude of the wave function. So to kind of give what I think is a little bit more of an intuitive description here, we'll say we have C1, and we're going to draw stairs, and C1 is a ball sitting at the top. Here, let me make this a little smaller, that way I have room. So we're going to call this C1, which is the ball sitting at the top stair, plus C2, which is the ball sitting second step. What did I just do? On the second step, plus C3, which is the ball sitting on the third step. So this C1 is the ball is sitting on the top step. C2 is the ball is sitting on the next step down. And C3 is the ball is sitting on the next step down from that. So again, this here, you would take that C1 squared and square it, and that would give you the probability of this state being measured. So in reality, what you would have is, oh shit, what am I doing? What you have is, if I could draw a wave function or a psi properly, that would be great. 2, 3. Make that look. And the Born rule is telling you take the coefficient, which is generally a complex number, square that number, and that will give you the likelihood of that particular state, the state associated with that number being measured. And that is what the Born rule tells us. And when we do that, we're actually capable of making a measurement on the system. We're actually capable of deriving a quantity for the measurement that we're making. Team Skeptics Live, cool. Don't really care. So that is what the Born rule are. The normalization condition and the Born rule are, in my opinion, probably two of the most important aspects to a wave function, and using a wave function to figure out what a system is doing. Because like I said earlier, that's essentially what the wave function is. It's a tool that we use to figure out what a system is doing out of a set of possibilities of what the system could be doing. First, you need to normalize the wave function so that you know that all the probabilities of what the state is doing equal 1, and then you need to utilize the Born rule to figure out, okay, what is the probability assigned to each one of those potential quantities. And once you've done that, you can do some more fancy math, and you'll be able to figure out, okay, this is what my system is doing. A final concept that I want to introduce that is related to this is it sort of helps understand why we use wave functions, and that is, let me see if I can do this a little bit differently. There we go. Draw a line. Cool. We're going to draw a coordinate space here, but instead of these two lines being considered an axis, I kind of want you to forget about that for a second, and we're going to turn them into vectors. So now we need to put arrows on them. These vectors would be, in quantum mechanics, called a basis vector. And the reason for that is because any other vector defined between the two of these vectors could be written as a combination of those two. So if I drew a vector going up like that, ignore the curve, it's not supposed to have a curve. I can get two numbers that give the location of that vector, i.e. it's a combination of those two basis vectors. And that is what a basis vector is. I lost my arrow. Simplistically, that's what a basis vector is. So a wave function would be in a superposition of these two basis vectors. It's a combination of them. That is what superposition really is, and that was the concept that I wanted to introduce, superposition. So this is a good way of introducing, I think, intuitively what superposition is. This, the wave function, and that's just fancy mathematical notation for a wave function when you're mapping it as a vector on a space, more specifically a Hilbert space. That is what a wave function is. It's not here, but it's not here. It's between both of them. It is in a superposition of here and here. But you haven't made a measurement on it, so it doesn't actually have a defined value. And that is what superposition is. And this is part of the reason why we need to use wave functions, because we need to be able to define something in a superposition, and wave functions help us do that. Now, I probably shouldn't have done that. There's interesting things happen. Let me go back to black here. If you start projecting the state vector or the wave function onto your basis vectors, but I'm not going to get into that right now because that's an entirely different video that I want to do on the subject. That would relate to something some of you viewers might already know that is called wave. Here, let me write it out for you if I can not write with an eraser. Wave function wave function collapse, which is obviously related to the wave function, hence the term wave function and wave function collapse. But I want to do a separate video on that. This one was just to introduce what a wave function is, what it means, and how we use it in quantum mechanics. So just to recap, a wave function is a function that is defined by a complex number, which means it has both a real part and an imaginary part. We can derive what some system is doing utilizing the wave function, but we don't do it by utilizing the wave function purely. What we have to do is we have to take the coefficient associated with that wave function and square it, and that will give us the probability of that particular, the state associated with that particular wave function being measured. That is what a wave function is. That is what we use them for in quantum mechanics. And in the next video, I will go deeper into wave function collapse, because I think more people probably misconstrue what wave function collapse is than they do what a wave function itself is. But first, if I'm going to dive into wave function collapse, I want people to know what a wave function is and what they're used for. So three things actually that you should take away from this video is normalization condition. All the probabilities defined by a wave function must add up to 1. So draw equals 1. Born rule, or the probability of measuring some outcome is given by the coefficient tied to that outcome squared. You could really just say, I think it's actually more the absolute value squared. So you could just say the absolute value of psi squared. And superposition. Something is not actually in a measurable state until it's measured. Sounds weird. That's just quantum mechanics. Quantum mechanics is just fucking weird. So if there's 3 things to take away from this video, and perhaps maybe do your own research on, they would be the normalization condition. A little bit of integral calculus is going to be needed to really understand that in a mathematically rigorous manner. The Born rule, the Born rule can be understood mathematically. You really don't need to dive too much into the math to really understand what the Born rule is. And finally, superposition. So those are 3 things that I want you guys to think about as they relate to a wave function. Think about, okay, what a wave function is, and then maybe see if you can figure out what wave function collapse means on your own before we touch on that video. I'm going to try to do these once a week. Sometimes I might get bored and make a video early. Sometimes I might be busy and make it late. The first video I wanted to get earlier than 1 week after the introductory video, because the introductory video doesn't have much content in it. It's just introducing the series, letting you guys know that I'm doing the series. So I'm thinking next Wednesday I might do it earlier, I don't know. We will be touching on wave function collapse. But until then, think about what I've given you in this video and see if you can maybe figure out what wave function collapse is on your own. And until then, per causam nos perfectum, or through reason we progress.